1968, Racine, Wisconsin. The roar of diesel engines and hydraulic pumps echoed across the case factory floor as the first construction king rolled off the production line. A 3-ton integrated backhoe loader that European engineers had already dismissed as agricultural approach to construction equipment. German specialists claimed the unified frame design would sacrifice specialized performance. British trade publications predicted mechanical reliability issues with combined systems. Swedish manufacturers insisted that serious construction demanded separate, purpose-built machines. The Americans were building something the Europeans said would never work in professional construction. One machine, loader and backhoe integrated. Simple hydraulics any mechanic could repair. No computers, no sensors. No emission control systems, just straightforward engineering that prioritized field serviceability over technological complexity. 50 years later, on construction sites across America, an impossible contradiction was revealing itself. The machine that European engineers said would fail was still digging trenches while the advanced replacement sat broken. The acquisition papers for the Churubusco Corporation arrived at case headquarters in Racine, Wisconsin on a humid Tuesday morning in 1957. Inside the manila folder lay the blueprints for what would become the foundation of American construction equipment dominance, though the executives reviewing the documents had no way of knowing they were holding the future in their hands. The Churubusco team had cracked something that had eluded American manufacturers for decades: truly efficient hydraulically powered backhoe technology that could be integrated into existing agricultural tractor designs. Elton Long studied the hydraulic schematics with the methodical precision that had earned him respect from both the engineering department and the shop floor workers who actually built the machines. The Churubusco design eliminated the cable-operated systems that plagued existing excavators, replacing them with hydraulic cylinders that delivered consistent power and precise control. Long recognized immediately that this wasn't just an improvement, it was a complete reimagining of how earth-moving equipment could function. The post-war construction boom was creating demand that existing equipment simply could not meet, and every construction company in America was desperate for machines that could dig faster, move more dirt, and stay operational longer. The challenge facing Long and his team was integration. Churubusco had perfected the hydraulic backhoe, but it remained a specialized attachment. The construction industry needed something more versatile, a machine that could load trucks, dig trenches, and move materials without requiring operators to switch between different pieces of equipment. Long spent months sketching unified frame designs on napkins during lunch meetings, working out the stress points and hydraulic flow requirements that would allow a single operator to control both loader and backhoe functions from one seat. The breakthrough came when Long realized that the traditional approach of mounting separate systems onto tractor frames was fundamentally flawed. Instead of adapting existing designs, he proposed building an entirely new machine around the integrated concept. The frame would be purpose-built to handle the stresses of both loading and digging operations, with hydraulic systems designed from the ground up to power both functions efficiently. The result was a machine that weighed 3.363 tons with a 0.43 cubic meter bucket capacity and 4.267 meter digging depth, specifications that would define the backhoe loader category for decades. The hydraulic system Long designed operated at 1,500 pounds per square inch, utilizing straightforward split-piston cylinders that any competent mechanic could understand and repair. The power came from a 188 cubic inch non-turbocharged diesel engine, producing 50 to 60 horsepower, fed by a Rusa master fuel injection system that prioritized reliability over complexity. Every component was selected based on field serviceability rather than theoretical performance, reflecting Long's conviction that the best engineering solved problems without creating new ones. When the first pre-production models rolled out of the Racine facility in 1967, European manufacturers dismissed the American approach with barely concealed condescension. Dr. Heinrich Bauermann, whose analysis carried significant weight among German construction equipment circles, published a scathing assessment in European trade journals. The integrated design, he argued, represented a fundamental misunderstanding of construction equipment requirements. Professional applications demanded specialized machines optimized for specific tasks, not agricultural tractors masquerading as construction equipment. British engineering publications echoed Bowerman's skepticism, predicting that the combined stresses of loading and digging operations would create mechanical reliability issues that would plague American contractors. Swedish manufacturers, who had built their reputations on purpose-built excavators and loaders, insisted that serious construction work required separate machines designed specifically for each function. The Europeans had spent decades perfecting specialized equipment, and they viewed the American integrated approach as a naive attempt to cut corners that would inevitably compromise performance. The formal debut of the Case 580 construction king in 1968 should have silenced the critics, but European skepticism only intensified. The machine that American engineers had designed with pencil and paper calculations was outperforming European equipment that had been refined through generations of specialized development. Construction contractors across the United States began replacing their separate loaders and excavators with single machines that could handle both functions more efficiently than the specialized equipment they replaced. Long's design philosophy proved prophetic in ways that even he had not anticipated. By prioritizing simplicity and serviceability over technological sophistication, the 580 created a new standard for construction equipment reliability. Operators could master the controls in hours rather than days, and mechanics could diagnose and repair problems with standard tools available at any equipment dealer. Parts availability was never an issue because the components were designed around common industrial standards rather than proprietary specifications that required factory-trained technicians. The irony was lost on European observers who continued to dismiss American engineering as unsophisticated. The machine they characterized as overly simple was revolutionizing construction sites across America, proving that elegant solutions often emerged from understanding real-world requirements rather than pursuing theoretical perfection. The 580 represented something that European manufacturers had never seriously considered: engineering that served operators and mechanics rather than impressing competitors. As the 1970s approached, the implications of Long's achievement began to crystallize. The fundamental philosophy of American construction equipment, robust, serviceable, and operator-focused, had created a machine that would define an entire industry category. But even as the 580 proved its worth on construction sites from coast to coast, new challenges were emerging that would test whether simplicity could survive in an increasingly complex world. The 580 original model that entered full production in 1970 established a pattern that would define American construction equipment for the next 2 decades. Tommy Rodriguez, a young equipment operator working residential construction sites around San Antonio, discovered what thousands of contractors across the country were learning. The machine that European engineers had dismissed as overly simplistic was proving more reliable than equipment costing twice as much. Rodriguez could operate the 580 for 10-hour shifts without the mechanical failures that plagued more sophisticated competitors, and when problems did occur, he could often diagnose and repair them himself using basic tools carried in his truck. The 580B model, introduced in 1973, refined Long's original design without abandoning the core philosophy of mechanical simplicity. Case engineers resisted the temptation to add electronic systems or computerized controls that were beginning to appear on European equipment. Instead, they focused on improving the components that operators and mechanics actually interacted with daily. The hydraulic system remained straightforward and repairable, the transmission stayed manual or power shuttle without computer intervention, and the fuel injection system continued to use mechanical pumps that could be serviced at any diesel shop in America. By the time the 580C entered production in 1976, the machine had become the standard against which all other backhoe loaders were measured. The 207 cubic inch case diesel engine that powered the C model delivered consistent performance across a wide range of operating conditions, from the frozen construction sites of Minnesota winters to the dust and heat of Arizona summers. Construction and landscaping professionals embraced the C model because it combined the versatility they needed with the reliability their businesses demanded. Unlike European machines that required specialized training and factory-certified technicians, The 580C could be operated and maintained by anyone with basic mechanical knowledge. The hydraulic system design that Long had pioneered remained virtually unchanged through successive model iterations, and for good reason. The 1500 psi operating pressure provided sufficient power for demanding construction applications while staying well within the safety margins that prevented catastrophic failures. The split-piston cylinders delivered smooth and responsive operation that allowed operators to make precise movements, whether they were loading trucks or excavating utility trenches. Most importantly, the entire system was designed for field repair using standard hydraulic components available from industrial suppliers nationwide. Rodriguez and operators like him discovered that the 580's mechanical systems provided tactile feedback that electronic controls could never match. The direct connection between operator input and machine response created an intuitive understanding of equipment capabilities and limitations that made experienced operators significantly more productive. When hydraulic pressures dropped or engine performance changed, operators felt the difference immediately through the controls, rather than waiting for warning lights or computer diagnostics to identify problems. The 580D model, launched in 1981, incorporated incremental improvements while maintaining the fundamental design philosophy that had made the machine successful. Parts availability remained excellent because Case had standardized on common industrial components rather than proprietary systems that required special ordering and factory support. Any equipment dealer could stock the filters, seals, and wear items that kept 580s operating, and mechanics across the country had developed the expertise to service and repair the machines using standard shop equipment. The introduction of the 580E in 1985 marked the pinnacle of mechanical simplicity in American construction equipment. The machine retained manual transmission options for operators who preferred direct control over gear selection, and the hydraulic system continued to operate without computer intervention or electronic monitoring. The diesel engine remained naturally aspirated and mechanically fuel injected, eliminating the turbocharger and electronic systems that added complexity without improving reliability for typical construction applications. When the 580K entered production in 1987, it represented the final evolution of Long's original design philosophy before external pressures would force fundamental changes. The K model featured a Cummins four-cylinder diesel engine that built a reputation as one of the most reliable power plants in its class, delivering consistent performance across hundreds of thousands of operating hours without major overhauls. Construction companies discovered that 580K models could operate for decades with routine maintenance, accumulating work hours that would destroy more sophisticated competitors. The success of the K model validated everything that American engineers had learned about construction equipment design over the previous 2 decades. Simplicity translated directly into uptime, and uptime determined profitability for contractors whose businesses depended on equipment reliability. The machine that could be serviced by any competent mechanic with basic tools generated more revenue than sophisticated equipment that required dealer service calls and specialized diagnostic equipment for routine maintenance. Throughout the golden age of the 580, European manufacturers continued to pursue technological complexity as a pathway to market differentiation. German equipment featured elaborate hydraulic systems with computer-controlled flow management. Swedish machines incorporated advanced metallurgy and precision manufacturing techniques, and British designs emphasized specialized performance optimization for specific applications. Yet American contractors consistently chose the simpler, more serviceable Case machines over European alternatives that promised superior performance but delivered frequent breakdowns and expensive repairs. The contrast became particularly evident on large construction projects where equipment downtime affected entire work schedules. Projects using 580 machines experienced significantly fewer delays caused by mechanical failures, and when problems did occur, repairs could often be completed on site without waiting for factory technicians or special parts shipments. The economic advantage of reliable, serviceable equipment proved more valuable than the theoretical performance benefits of sophisticated European designs. Rodriguez, who had operated 580s for over a decade by the late 1980s, could perform most routine maintenance and minor repairs himself, keeping his machine operational when competitors' equipment sat idle, waiting for service appointments. The knowledge he had accumulated about hydraulic systems, diesel engines, and mechanical transmissions made him more valuable to employers and more profitable as an independent contractor. The machine had taught him skills that applied across the entire construction industry, rather than limiting him to proprietary systems that only factory-trained specialists could service. As the 1990s approached, the 580 represented the culmination of American construction equipment engineering philosophy. The machine worked because it was designed by people who understood that real-world construction sites demanded reliability above sophistication, serviceability above performance, and practical solutions above theoretical elegance. But forces beyond the construction industry were already gathering that would challenge everything the 580 represented. The first warning signs arrived in Washington during the early 1990s, buried in Environmental Protection Agency reports that most construction equipment manufacturers initially dismissed as regulatory overreach. The Clean Air Act amendments targeted diesel emissions with increasingly stringent standards that would fundamentally alter the engineering principles that had guided American equipment design for decades. EPA scientists, armed with atmospheric data and public health studies, began crafting regulations that would eventually force every diesel engine in America to incorporate computer-controlled systems that prioritized emissions reduction over mechanical simplicity. Tommy Rodriguez noticed the changes gradually as he moved between different construction sites throughout the mid-1990s. Newer equipment arriving on job sites featured electronic fuel injection systems that replaced the mechanical pumps he understood, and exhaust gas recirculation systems that introduced complexity into diesel engines that had operated reliably for generations without computer intervention. The Tier 1 emission standards implemented in 1996 seemed manageable at first, requiring modest modifications that didn't significantly impact field serviceability or operator familiarity. The transition accelerated when Tier 2 standards took effect in 2001, mandating further reductions in nitrogen oxide and particulate matter emissions that could only be achieved through sophisticated aftertreatment systems. Equipment manufacturers began installing diesel oxidation catalysts and more advanced electronic control modules that monitored dozens of engine parameters in real time. Rodriguez discovered that newer machines required diagnostic computers to identify problems that he had previously diagnosed through direct observation and mechanical knowledge accumulated over years of hands-on experience. Case engineers faced an impossible choice as Tier 3 regulations approached in the mid-2000s. They could maintain the mechanical simplicity that had made the 580 successful and accept that their machines would no longer meet federal emission standards, or they could embrace electronic complexity and fundamentally alter the character of equipment that contractors had trusted for decades. The decision was made for them when EPA enforcement became unavoidable around 2008, forcing the integration of exhaust gas recirculation and electronic injection systems that required computer control to function properly. The promise of modern technology seemed compelling during the early implementation phase. Equipment sales representatives demonstrated fuel economy improvements of 15 to 20% compared to older mechanical systems, and emissions reductions that satisfied both environmental regulations and corporate sustainability initiatives. Construction companies that had resisted computerization discovered that government incentive programs made upgrading to cleaner equipment financially attractive, especially when combined with manufacturer warranties that promised reliable operation of the new systems. Advanced telematics systems introduced alongside emissions controls offered fleet management capabilities that had never existed in mechanical equipment. Construction companies could monitor machine location, operating hours, fuel consumption, and performance parameters remotely, optimizing equipment utilization and scheduling maintenance based on actual operating conditions rather than arbitrary time intervals. The integration of GPS technology and automated functions promised to reduce operator fatigue and improve productivity on complex construction projects. The hydraulic systems accompanying electronic engines became increasingly sophisticated with computer-controlled flow management that optimized performance based on load conditions and operator input. Manufacturers claimed that electronic control could deliver superior response characteristics compared to mechanical systems, automatically adjusting hydraulic pressure and flow rates to match specific applications. The theoretical benefits were impressive: faster cycle times, reduced fuel consumption, and consistent performance regardless of operator skill level. Equipment manufacturers celebrated the technological transformation as evidence of industry innovation and environmental responsibility. Trade publications featured articles about smart machines that could diagnose their own problems, optimize performance automatically, and reduce the skill requirements for effective operation. The narrative suggested that construction equipment was finally catching up with the digital revolution that had transformed other industries, delivering benefits that mechanical systems could never achieve. Government agencies provided regulatory support for the transition through purchase incentives and emissions compliance programs that encouraged early adoption of advanced technology. The EPA promoted Tier 4 regulations as necessary for public health protection, emphasizing that diesel particulate matter and nitrogen oxide emissions contributed to respiratory diseases and environmental degradation that justified the complexity required for compliance. Environmental groups praised equipment manufacturers for embracing cleaner technology that would reduce the construction industry's impact on air quality. The integration of diesel particulate filters around 2008 introduced the first serious operational complications that foreshadowed larger problems ahead. DPF systems required periodic regeneration cycles that burned off accumulated particulate matter at temperatures high enough to create potential safety hazards on construction sites. Operators discovered that regeneration cycles could interrupt critical work, forcing equipment shut down at inconvenient times when construction schedules demanded continuous operation. Rodriguez experienced his first taste of the new complexity when a DPF sensor failure triggered a fault code that limited his machine to reduced power output, eventually forcing him to stop work entirely until a dealer technician could diagnose and repair the problem. The mechanical knowledge that had served him for decades became irrelevant when faced with the electronic systems that required proprietary diagnostic equipment and factory-trained specialists to service properly. The repair cost more than he typically spent on maintenance in an entire year, and the downtime affected his ability to complete contracted work on schedule. The early implementation of Tier 4 standards revealed the fundamental conflict between emissions compliance and operational reliability that would define the next decade of construction equipment development. Engines producing up to 75 horsepower could avoid diesel exhaust fluid requirements, but still required diesel particulate filters that introduced failure points unknown in mechanical systems. Higher horsepower engines needed selective catalytic reduction systems with DEF injection that added another layer of complexity and potential breakdown modes. Warning signs emerged as the technology matured and accumulated operating hours in real-world construction environments. Service complexity increased exponentially as diagnostic procedures required specialized equipment costing thousands of dollars that only authorized dealers could afford to purchase and maintain. The intimate knowledge of hydraulic systems and diesel engines that had made experienced operators valuable became obsolete when computers controlled every aspect of machine operation and malfunction diagnosis required electronic interfaces rather than mechanical understanding. The transformation was irreversible once manufacturers committed to electronic control systems and aftertreatment technology. The simple, serviceable machines that had defined American construction equipment excellence became impossible to produce legally, replaced by sophisticated systems that promised superior performance but delivered unprecedented vulnerability to catastrophic failures that could disable expensive equipment for extended periods. The JCB models rolling off production lines in 2015 represented the pinnacle of what modern engineering could achieve when regulatory compliance and technological sophistication merged into a singular vision. The Tier 4 final engines ranging from 74 to 109 horsepower incorporated selective catalytic reduction systems using diesel exhaust fluid that reduced nitrogen oxide emissions by 90% compared to earlier generations. Equipment sales representatives demonstrated fuel efficiency gains that seemed to vindicate every prediction about advanced technology delivering superior performance while meeting environmental standards that had once seemed impossible to achieve. The hydraulic systems accompanying these engines featured computer-controlled flow management that automatically optimized pressure and volume based on load conditions detected by dozens of sensors throughout the machine. Operators discovered that the electronic controls could deliver cycle times faster than mechanical systems, with automatic adjustments that compensated for varying soil conditions, operator technique, and hydraulic fluid temperature. The integration of GPS positioning and automated functions promised to reduce operator fatigue while improving accuracy on complex grading and excavation projects that demanded precision impossible with purely mechanical control. Construction equipment dealers across America celebrated the technological transformation as validation of decades of research and development investment. The sophisticated diagnostic systems could identify potential problems before they caused catastrophic failures, alerting operators and fleet managers to maintenance needs through telematics systems that monitored machine performance continuously. Advanced metallurgy and precision manufacturing techniques borrowed from European designs delivered components that exceeded the durability standards of mechanical predecessors while operating under computer control that optimized performance parameters in real time. Trade publications heralded the arrival of the smart machine era, with feature articles showcasing construction sites where GPS-guided equipment operated with accuracy measured in millimeters rather than inches. Automated functions could maintain precise grade control without constant operator intervention, and computer-controlled hydraulics delivered consistent performance regardless of operator skill level. The promise extended beyond individual machine capabilities to integrated fleet management systems that could coordinate multiple machines on complex projects while monitoring productivity metrics impossible to track with mechanical equipment. Government agencies provided regulatory framework and financial incentives that encouraged rapid adoption of the advanced technology. Environmental Protection Agency officials emphasized the Tier 4 final standards represented necessary progress towards sustainable construction practices that would reduce the industry's impact on air quality and public health. Federal tax incentives and state purchase programs made upgrading to cleaner equipment economically attractive for construction companies that had previously resisted the transition from mechanical to electronic systems. The construction industry embraced the environmental responsibility narrative with enthusiasm that reflected genuine commitment to reducing diesel emissions and improving workplace safety. Corporate sustainability initiatives highlighted the adoption of advanced equipment as evidence of environmental stewardship that aligned with broader social expectations about industrial responsibility. Construction companies discovered that clients increasingly preferred contractors using cleaner equipment, creating market advantages for early adopters of sophisticated emissions control technology. Advanced telematics systems delivered fleet management capabilities that transformed how construction companies operated and maintained their equipment. Real-time monitoring of fuel consumption, operating hours, and performance parameters allowed managers to optimize equipment utilization and schedule maintenance based on actual operating conditions rather than arbitrary time intervals. The data collection capabilities provided insights into operator behavior and machine performance that enabled productivity improvements impossible with mechanical equipment that generated no electronic records. Tommy Rodriguez, now approaching 2 decades of equipment operation experience, initially found the sophisticated controls intimidating, but gradually appreciated the performance advantages they delivered. The computer-controlled hydraulics responded more precisely than mechanical systems, and the automated functions reduced the physical demands of operating heavy equipment for extended periods. Fuel efficiency improvements translated directly into lower operating costs, and the diagnostic capabilities provided advance warning of maintenance needs that prevented unexpected breakdowns during critical work periods. The integration of advanced emissions control systems seemed to validate the regulatory approach that had driven technological development throughout the 2000s. Diesel particulate filters achieved 90% reductions in particulate matter emissions, while selective catalytic reduction systems virtually eliminated nitrogen oxide emissions that had made diesel engines environmental targets. The technology delivered measurable air quality improvements in urban construction environments, where previous generations of equipment had contributed significantly to local pollution levels. Manufacturers invested billions of dollars in research and development programs that pushed the boundaries of what was possible with diesel engine technology and computer control systems. The sophistication of modern construction equipment rivaled aerospace and automotive applications, incorporating sensors and processing capabilities that would have been considered impossible just decades earlier. Engineering teams celebrated achievements that combined environmental compliance with performance improvements that exceeded the capabilities of mechanical predecessors. The early operational experience with Tier 4 final equipment seemed to confirm every prediction about advanced technology delivering superior results. Construction sites reported improved productivity, reduced fuel consumption, and environmental compliance that satisfied both regulatory requirements and corporate sustainability goals. Equipment dealers documented customer satisfaction with diagnostic capabilities and automated functions that simplified complex operations while delivering consistent results, regardless of operator experience level. Industry conferences and trade shows showcased the technological achievements with demonstrations that highlighted the precision and efficiency possible with computer-controlled equipment. Manufacturers competed to display the most advanced features, from GPS integration and automated grading functions to predictive maintenance systems that could schedule service appointments based on component wear patterns detected through continuous monitoring. The future of construction equipment seemed clearly defined by increasing sophistication and electronic control that would eventually eliminate the variability and limitations associated with mechanical systems. The validation appeared complete when major construction companies began replacing their entire fleets with modern equipment that promised decades of reliable service supported by comprehensive warranty programs and dealer service networks equipped to handle the complexity of advanced systems. The transition from mechanical to electronic control represented more than technological evolution. It embodied a fundamental shift in how construction equipment would be designed, operated, and maintained for the foreseeable future. Yet beneath the celebration and industry enthusiasm, subtle warning signs were beginning to accumulate among operators and mechanics who understood that complexity always carried costs that were not immediately apparent. The sophisticated systems that promised superior performance were creating dependencies on electronic components and specialized knowledge that would prove far more fragile than the mechanical systems they had replaced. The true test would come when the advanced technology encountered the harsh realities of construction site operation over extended periods. The diesel exhaust fluid sensor failure that crippled Rodriguez's brand new backhoe on a Tuesday morning in March 2021 epitomized a crisis that was spreading across construction sites throughout America. The machine's computer system detected what it interpreted as contaminated DEF and immediately triggered a countdown sequence that would limit the equipment to 5 miles per hour within 4 hours of the initial alert. No amount of mechanical knowledge could override the electronic lockout, and the nearest authorized dealer was booked solid with similar emergencies for the next 6 days. The Environmental Protection Agency's own internal reports, released reluctantly after industry pressure reached crisis levels, admitted that sensor failures in diesel exhaust fluid systems could be catastrophic, causing significant disruptions in logistics, agriculture, and construction sectors. The sensors designed to monitor DF quality and quantity proved vulnerable to contamination, temperature extremes, and vibration that were routine conditions on construction sites. When sensors failed, the sophisticated computer systems interpreted the malfunction as emissions violations and shut down equipment to prevent regulatory noncompliance. Rodriguez discovered that the $200,000 machine sitting idle in his equipment yard had become a monument to technological hubris. The diesel exhaust fluid that was supposed to enable clean operation proved chemically unstable when exposed to temperature fluctuations common in construction environments. DEF crystallized in cold weather, clogging injection nozzles and triggering fault codes that required dealer intervention to clear. In summer heat, the fluid degraded chemically and triggered contamination alarms that forced equipment shutdown until the entire system could be flushed and refilled with fresh fluid costing hundreds of dollars per service cycle. The selective catalytic reduction systems that had promised 90% emissions reductions created failure modes that mechanical systems had never experienced. SCR catalyst substrates proved vulnerable to thermal shock when equipment operated under varying load conditions, and catalyst poisoning from fuel additives or hydraulic fluid contamination could disable the entire aftertreatment system permanently. Replacement costs often exceeded $10,000, and the specialized components required factory ordering with delivery times measured in weeks rather than days. Diesel particulate filter regeneration cycles began interrupting critical construction work with increasing frequency as the systems accumulated operating hours and soot loading patterns that differed from laboratory test conditions. The regeneration process required sustained high exhaust temperatures that were difficult to achieve during typical construction operations, leading to incomplete burn-off cycles that gradually clogged the filters. When passive regeneration failed, operators had to initiate active regeneration cycles that could take up to an hour and generated exhaust temperatures hot enough to create fire hazards on construction sites with combustible materials. The contrast between modern equipment failures and the reliability of older machines became impossible to ignore as construction companies tracked downtime statistics that revealed troubling patterns. Vintage Case 580s from the 1970s and 80s continued operating with annual downtime averaging 2 to 3 days for routine maintenance, while modern Tier 4 equipment experienced 15 to 25 days of downtime annually due to emission system malfunctions. The sophisticated diagnostic systems that were supposed to prevent problems instead created dependencies on dealer service calls that cost $150 per hour plus travel time and parts markup. Equipment dealers struggled to maintain adequate inventories of electronic components and specialized fluids required to keep modern machines operational. DF consumption averaged 2 to 4% of fuel usage, requiring regular replenishment with fluid that had limited shelf life and required careful handling to prevent contamination. The storage and distribution infrastructure for diesel exhaust fluid proved inadequate for construction sites in rural areas, forcing contractors to maintain their own storage systems and accept responsibility for fluid quality control that could disable equipment if mishandled. The urea that formed the active ingredient in diesel exhaust fluid introduced chemical hazards that had never existed with mechanical equipment. Liquid urea was classified as corrosive and could cause severe burns if it contacted skin or eyes during handling. When heated, urea decomposed into ammonia gas that presented respiratory hazards in enclosed spaces. The powder form of urea was explosive under certain conditions, creating storage and transportation challenges that complicated fleet management for construction companies operating in remote locations. Major manufacturers began issuing recalls in 2021 as the scope of emission system failures became undeniable. Caterpillar recalled thousands of machines due to faulty nitrogen oxide sensors that could trigger false emissions violations. John Deere acknowledged SCR system failures that had disabled equipment across multiple model lines. The recall notices revealed design flaws in electronic components that had passed laboratory testing, but failed under the vibration, temperature, and contamination conditions routine on construction sites. Tommy Rodriguez watched his business suffer as the reliable income stream he had built over 2 decades evaporated due to equipment that prioritized regulatory compliance over operational availability. The mechanical knowledge that had made him valuable to contractors became irrelevant when faced with electronic systems that required proprietary diagnostic equipment and factory-trained technicians. Simple problems that he could have repaired in the field with basic tools now required dealer service calls that consumed entire workdays and generated repair bills exceeding his monthly equipment payments. The Environmental Protection Agency began quietly extending derate timelines and modifying enforcement procedures as industry complaints reached levels that threatened regulatory credibility. New DEF system protocols implemented in 2024 allowed up to 650 miles of operation before performance limitations took effect, acknowledging the downtime risk that earlier regulations had ignored. The modifications represented tacit admission that emissions compliance had created operational problems more severe than the environmental issues the regulations were designed to address. Construction companies responded to the reliability crisis by actively seeking pre-emissions equipment that could provide dependable service without the complex aftertreatment systems required on modern machines. Used equipment dealers reported unprecedented demand for 1990s and early 2000s backhoes that incorporated basic electronic controls without the vulnerable emission systems. Case 580K models from the late 1980s commanded premium prices despite their age, with examples in good condition selling for $15,000 to $25,000 to contractors desperate for reliable equipment. The market spoke with unmistakable clarity about the value of mechanical simplicity versus electronic sophistication. Construction companies that had embraced advanced technology found themselves maintaining fleets of backup equipment from earlier eras to ensure project completion when modern machines failed. The revelation that 50-year-old equipment designed with slide rules and mechanical knowledge could outperform computer-controlled successors represented a fundamental indictment of regulatory approaches that prioritize theoretical compliance over practical functionality. Rodriguez realized that the industry had sacrificed operational reliability for environmental compliance in ways that ultimately served neither goal effectively. The sophisticated machines that consumed enormous resources during manufacturing and generated complex waste streams during disposal might actually create larger environmental impacts than the simpler equipment they replaced, especially when downtime forced contractors to maintain redundant fleets to ensure project completion.